So last time we started with, and we had a very small example of algorithm. So it is, this is a definition, step-by-step procedure of solving problem in a finite amount of time. Now this we already discussed, so I'm going to skip. Then how, now another thing is when we are talking about time complexity. So space complexity, we discussed that nowadays it is not such a big issue. Now we are going to calculate time complexity. So what will be the ideal case and how can we calculate time complexity? So if you look at three algorithms, let's say I have three algorithms. What is the ideally we should be calculating? So I have to calculate which algorithm is good. So let's say I have three algorithms that I have developed, A1, A2, A3. Now, ideally, what should we do is we should implement this algorithm all. So we should implement all algorithms and maybe we will have some input size n. Okay, so some input size, and then we will have to check how these algorithms are behaving when the input size grows. So maybe we can plot a graph where these are my three algorithms, and then this is my input size n. So as n grows, how much time each algorithm is taking. So let's say n here is, if my input size is 10, might be 100, then 1000, 10,000, and so on. And it keeps growing. Now, if I have my A is running, and this might be time in, let's say, milliseconds. Now the machines have become faster, so we can, let's say, milliseconds. So let's say, and I will also have some scale here, 10, 100, 1000, 10,000, 1 million. So if my A1, if it grows, let's say this way. So I see that maybe for 100 input size, it is taking 100 milliseconds. For 1000, it is taking, let's say, 1000. For 10,000, let's say it is taking 10,000. For 1 million, it is, let's say, taking 1 million. So whatever is my input size, my output size is same. Sorry, my time taken to execute that algorithm is same. So this is also called as a linear growth. So it is growing in exact same proportion to my n. Now that might be, sometimes it might be half, meaning that for my input 10, I might have 5 milliseconds. For 100, might be 50. For 1000, might be 500. So if that is the case, then you will see that the points will be little different, right? So let's say something like this. But if you look at the growth rate, it is still going to be similar, right? Meaning that it is still linear. And after, when, let's say, my input size becomes billion or tens of millions, it will no longer matter whether it is n or whether it is n by 2. The growth rate will look, after a certain point, these two lines are going to run parallelly if they both are dependent on input size and they are growing in a linear fashion for the input size. So now that is one possible scenario. Now let's say I have another algorithm A2 that we implemented and that we are executing. Now A2 is taking, let's say, for 10, it is taking 100. For 100, it is taking 10,000. For 1,000, it is taking 1 million. Okay. So the growth will be something like this. So we are basically trying to figure out the proportion of what is my n to what time we are taking. So in with respect to A1, we saw that whatever was n, exactly same time it is taking. So it is kind of, we can say, proportional in terms of n. If we are talking about A2, we are saying that if n is 10, my A2 is 100. If A2 is 100, it is 10,000 and so on. So it is, if it is 1,000, it is 1 million. So we can say the growth rate is in terms of n square. Because if my input is 10, I'm taking 100 milliseconds. If my input is 100, I'm taking 10K milliseconds. If my input is 1,000, I'm taking 1 million milliseconds. So it is growing in terms of n square. So it is, we can say, proportional to n square. Now let's say there is another, our last algorithm, A3, and when we executed that, we saw that for 10, it is taking 2 milliseconds. For 100, it is taking 4, or maybe let's say for 10, it is taking 1, for 100, it is taking 2, for 1,000, it is taking 3. Okay. So if you look at that graph, that is going to grow very, very slowly, not even this growth, very, very slow growth. And then maybe we can say that this is not even n. So this is not even linear, and that might be log n. So log n might be the time. So ideally, when we are comparing algorithm, we should implement all algorithm and then execute it for different values of n. That will give us the correct measure of, or give us the correct analysis. But if you look at it, is it going to be practically possible that all the algorithms we are developing, we have to implement, then we have to run it for different values of n? It is going to be so much time taking. Another thing, we might have to consider that all these algorithms are to be executed on the same machine. Because if I execute A1 on one machine and let's say A2 on another machine, which is much faster than A1, then I might see a different graph altogether. So assuming that all the hardware is same, assuming that we are doing it with the same capability of machines, possibly same person is executing all the things with same values of n, which is highly impossible to do. So this approach, although very accurate, it is not really practically possible. So what we are going to do is we are going to compute it theoretically. So we are going to come up with algorithm and we are going to predict how many times or how many operations this algorithm will run. And let's say at n, it is running 10 operations. Then it doesn't matter whether it is running it on faster or slower machine. It is going to run 10 operations. Algorithm A2, that maybe the total operations are 1,000, then we can say it is much worse than A1 and so on. So instead of actually implementing, we are going to learn theoretical analysis to compare the algorithm. So without implementing, we are just going to check how can we do this. So ideal approach will be write a program to implement the algorithm, run the program with various inputs that we discussed, and then use something which will, for every method, it will give you the time it took to execute. So something, some function like system.current time millis, it will give you for every execution how much time in milliseconds it took. That will give you correct running time, and then we plot the results, and then we decide which one is better. So here the input size goes from 0 to 100, and these are time in milliseconds. And if you look at this graph, let's say this is algorithm A1, A2, A3. Which one is the most efficient algorithm, do you think? A3. So now this is kind of, so whichever has more growth rate, whichever algorithm has more growth rate, that algorithm is less efficient. So we are ideally looking at algorithm which is growing at a slower pace or having slower growth rate. So if the growth rate is slow, it means the algorithm is efficient. If the growth rate is too high, it means for the input size, it is giving as the input grows, we are getting worse and worse results. So you will see that it doesn't initially for some values you will see that it doesn't really make that much difference. So for example, if I show some algorithm runs in n, some in n square, if n is equal to 1, it's not is a big difference. Both are going to take 1 milliseconds. When n is equal to 2, this is 2 and 4, again not much difference. But when I make n as 100, you will see more difference and so on, right? So as my n grows, then you will realize that whether the algorithm is better or worse, because after our n grows or goes beyond certain point, you will see that the algorithm grows much at a much higher speed than we don't want to use that algorithm. So generally, these are some observations. So most algorithms, what we are implementing, we will get some input from the user and we will generate some output for that input. Then assuming that for every input, as my n increases, as my input size, so number of inputs, so n here onwards, we are going to consider input size. Okay. So as my input size increases, so for example, when we were trying, let's say summation series. So here when n is equal to 10, we are adding 10 numbers. When n is equal to 100, we are adding 100 numbers. Okay? So definitely when we are adding 10 numbers, my time will be less than when we are adding 100 numbers. When my n becomes 1000, we are adding 1000 numbers and so on. So that is our input size, and maybe our whatever output or whatever the addition we get, that is our output. So typically we will see that for every algorithm, we will have some running time. And here another thing is that for some algorithm, there will be different cases. So if you are looking at specifically sorting, let's say. So let's say there are different sorting algorithms that we are plotting. And in that case, if the given input is already sorted, then the time we are going to take is much less. So that we can call it as a best case scenario. Then if half of the input is sorted and half is not, then in that case, some work we have to do, but that is not as bad. So we call that kind of a situation maybe average case scenario. And if all the numbers are in the descending order and we have to make it in the ascending order, then every two elements we have to swap. So whatever the time taken will be the worst case scenario. So we can also look at it as every algorithm does have some scenarios at which it will have less time, some scenarios at which it will take more time. Now how are we going to compare different sorting algorithms? So if we have to compare, then to be on a same platform, what you have to give is give same input, give sorted input to all the sorting algorithms, then give descending order input to all the sorting algorithms, give average to all. And then there are a lot of confusion about what is average. I might consider the first few elements sorted and remaining not is average. Somebody might consider the opposite way, right? So there is no one way to agree on how we can actually do it. So ideal scenario is actually considering average case, because not always the algorithm will take worst time. It might take best time, it might take average time, but there is a lot of confusion regarding what is average. So we cannot really find what is average. Now finding worst case scenario is much easier, because we should know that that condition might occur when we are designing algorithm. So better to design considering the worst case scenario rather than the best case scenario. Now, the best case scenario, all the numbers are already sorted. Now, it is very unlikely to happen that scenario, right? And if I'm designing an algorithm which is taking very less time for the best case scenario, let's say for best case scenario, it is taking log n, and for worst case scenario, it is taking n square. Then I have another algorithm too. For best case, it is taking n, and for worst case, it is taking n square. Now tell me which one is better. So this is best, this is worst. Okay, so which one should I implement? A1 or A2? A2. A2. So you will see that most of the times we will have to go with that those things at the worst what can happen. Okay, so that is that acceptable for me? Then we'll go with that algorithm. So here, while calculating, we are going to calculate the worst case scenario, assuming that if there if every operation that is required is done, then how bad it can go. And when we get that limit, that's the worst limit we can go. So we are in a better position to then find out efficiency of different algorithms. So we are going to focus on worst case running time. Why? Because it is easier to analyze and it is very crucial for different applications because they might run into the worst case scenarios quite often. Now, this will kind of discuss the limitations of doing it by actual implementation. So that's why we are coming to theoretical analysis. So how do we do theoretical analysis? We use the algorithm that we studied last time. So every problem we solve step by step, and it is in our algorithm format. And now we are going to see how many operations or in terms of n, how bad this algorithm goes. And we are going to characteristic the input size every time as n. We'll take into account all possible inputs, and it will allow us to give number of operations. Now, again, we are not going to focus on the speed dependent on memory, but actual number of operations. So here, pseudocode we saw last time, here is a different pseudocode. So let's say we have given an array of n numbers, and out of those n numbers, we have to find a maximum number. So this is a very easy approach. We have seen this in 336. So if we have some elements, let's say 2, 10, I don't want it to be in a single order. So if we have to find the maximum number in this particular array A, then the algorithm assigns the very first number as maximum. So this is my array A. So this element will be A of 0, A of 1, A of 2, A of 3, and A of 4. Now, if I have to find out the maximum from this array element, there are now different algorithms. So this is the simplest one. You go linearly. You assign the very first element as maximum. So my maximum is A of 0. Now you will go through each element and check. Whenever you find an element which is greater than the already assigned value of max, we are going to swap. Otherwise, we are going to keep it as it is. So we are going to compare all the elements with max. So the next element is A1. So we are going to check if maybe a for loop is needed. So for, let's say I is equal to 1, I less than n, I plus plus, we are going to check if max or if A of I is greater than max, then you switch max. If this is the case, then my max becomes A of I. Otherwise, it will stay as it is until it compares with all the n elements. So when we run it for the first time, this max is equal to 2. Next time, my I is equal to 1. So we are going to compare max with A of 1. So we are going to check if A of 1 is greater than max. Yes, no. 10 is greater than 2. Right? 10 is greater than 2. So we are going to swap. So now my max becomes A of 1. Then for the next value, it increments by 1. For next value, for A of 2, is A of 2 greater than max? No. So this is 8. It is going to skip. Now next value, is A of 3 greater than max? Yes. So it will swap and it will make max as A of 3. Now we are going to check next value, is A of 4 greater than max? No. So whatever is the value of max, that retains, which is equal to 60. So if we have to perform this kind of algorithm, so how many operations will be needed? So in terms of, if we have to calculate the number of operations, so here they have done it little differently. So if you have such algorithm, so the same algorithm, you will see that the input is array A of n integers, output is maximum. So initially we assign A of 0 as current maximum. And then for loop, which goes from 1 to n minus 1, we are going to compare. So this is, I think, n minus 1 is index. So our index start from 0 to n minus 1. So if A of I is greater than max, then you save it as current max and return. So this is a typical algorithm representation where instead of generally it will return the value, assignment will be shown by arrow, but we can also use the equal sign and for loop, which goes from 1 to n minus 1. So this is now a kind of a structured algorithm, and then we can actually calculate the number of operations it will take. And same thing we are going to do with other algorithm, and then we want to decide which algorithm takes less number of operations. So again, I said it uses pseudocode and algorithms as same. So here it is pseudocode, here is the algorithm, but it is the same thing. So what are the things which are acceptable? So as I said, when we are writing algorithm, we should not write anything which is language specific. So we will not write scanf, printf, we will not use semicolon, quotes, all those things. But we are allowed to use if, then, else, while, do, repeat, until, for, to. So this is a, you can say, standard structure to use in algorithm. And general algorithm is shown as algorithm method, whatever are the arguments of that method, whatever is input, whatever is output, and pretty much whatever we are able to write in program, we can also show it in terms of algorithm. Then if we have to call any method, then we can say this dot method you call a return value, return expression. If we want to use assignment, this is equal to this, we can. So here they have used arrows. We can also use is equal to in this scenario. We can also use current max is equal to A of 0. But this is a more standard way of doing it. You will see it in books a lot. Then equality testing, and they are using this for equality for algorithms in book, but we can as well use equal to and equal to. Then superscripts as you prefer. Now this is kind of whenever we are talking about operations, what is happening is a CPU is, so whenever I say I is equal to 2, it is accessing, it is storing the value in a memory So there is some kind of, you can say, time allocated for that. So go receive this variable, store it at, access the memory cell and store it there. Or even if we are retrieving it, access the memory cell and retrieve it. So that is all are considered as unit time. So considering that accessing memory takes 1 unit. So here we are not, maybe in reality it might take 1 microseconds, 1 millisecond, but we are not calculating in terms of um, actual time. So we are calculating in terms of number of operations. So assuming that takes unit time. And if we have some functions, now we will come to this chart again and again. So in the next class also we'll come to this. So if you look at the algorithm, how it is running. So if for any input size, it is taking constant time. Now, the constant time might not be 1. It might be for any input size, if it is taking 50 milliseconds, then we can, if we plot it on a graph, it is going to look like a straight line. So that is called as algorithm running in constant time. Sometimes the algorithm run in log time, like binary search. Sometimes it is proportional to n, sometimes n log n, n square, n cube, 2 raised to n. So if the algorithm is running in these respective times, then how the graph will look like if it is plotted. So that's the example. And these 7 functions we will come across again and again. So you will see that we are going to come across these in most of the algorithms. It will be one of these, or maybe if you have multiple for loops, then combination of these two, and that is more common. So now this is an analysis. So if you decide, if we want to find out this algorithm runs, or what is the running time of this algorithm, so maybe storing it and taking the value and storing it takes 1 unit. I think I had somewhere 8 n. So if we are counting primitive operations, so we in terms of memory, whatever value we are accessing, that is 1 unit. So 1 unit to access current max, 1 unit to access a of 0 and assign it to them. So that is number of operation 2. Now here again we are accessing I and assigning it to 1, accessing I, assigning it to. So if it goes from 1 to n minus 1, it will be twice. It is something, I think, twice n minus 1. And if for this, let's say it is, if a of I greater than current max, then current max is equal to this. So again, we are going to access these two variables. Again, here we are accessing these two variables. So the number of variables multiplied by 2, number of variables multiplied by 2. Every time we are going to increment the counter I, for that we are going to increment n minus 1 times, so twice of that. So whatever the operations might be little bit here and there, but it will be in terms of n. So you might, let's say 2, let's say we'll calculate here 2 n minus 1. Here, let's say 2n minus 2, 2n minus 2, 2n minus 2. How many times we are going to increment? Let's say we are incrementing n minus 2 times. So if we calculate this, or if we add all those operations, it will be something in terms of n. So here it is n, 8n minus 2, we might get 6n minus 5 or so. So assuming we did it little differently, but it will still be in terms of n, and that is more important. So if we have you can say a very basic rule, if we have one for loop which goes from 1 up to n or 1 up to n minus 1, then the time complexity is proportional to n. So whatever is we are going to execute it n times, no matter what. So whatever is inside operations, whatever value it gives me, it is in terms of n. If I have two for loops, it will be in terms of n square if both run from 1 to n. So here, if you calculate the number of total operation, it will be in terms of n. So we say that the time complexity is big O of n. Okay. So big O, we will see that, don't worry about that. But right now you remember that it is proportional to n because everything is going to run in terms of n.